So the goal of this video will be to walk through the proof of the asymptotic distribution of the maximum likelihood estimator. And so in class we listed several properties of the MLE, and this last one, asymptotic normality, kind of ties a few of them together. So it says that the maximum likelihood estimator, so our notation for that is theta hat. Sometimes we put an n to emphasize the dependence on sample size, is asymptotic normal, centered at the true value, and with variance equal to the Cramer-Rao lower bound for the parameter theta. So we're going to spend some time working up to a proof of this, and then we'll also see in class that asymptotic normality implies some of these others, for example, consistency. And one reason why we might care about asymptotic normality is it's important for doing statistical inference. So if you believe that you have a large enough sample size so that the distribution of your maximum likelihood estimator is approximately normal, then you can use that fact to, say, construct confidence intervals or develop a hypothesis test. Of course, that depends on the assumption that your sample size is large enough so that the approximate distribution really is close enough to the asymptotic distribution, and that really depends on the context. All right, so we'll do this proof of asymptotic normality in parts, and we'll always be relying on these regularity conditions that we spelled out in class. So the first thing that we'll do is note that just some notation. So theta star is the true value of theta. So we can think of theta as the variable and theta star as the specific true value that generated the data. And we want to show that if we have this equation here, which you can maybe identify as part of a Taylor series, part of a Taylor expansion, then if we have this, then that implies this equation here on the right. And once we have this equation here, you'll note that the left-hand side is the maximum likelihood estimator minus the true value times the square root of n. We're going to be able to show that this converges in distribution somewhere based on Slutsky's theorem, because we'll show that the numerator converges somewhere, the denominator converges somewhere in distribution and probability respectively, and so the whole thing will converge in distribution somewhere based on Slutsky's theorem. So we're going to go through all those details. The first step is really just to start out with this equation and show this one. All right. Well, the important thing to note here is that if we take the log likelihood function, so this script L notation is the log likelihood function. So if we take the derivative of that and we plug in the MLE, this should be equal to 0. And that's by definition, basically. So in these problems under regularity conditions, we find the maximum likelihood estimator by taking the derivative of the log likelihood and setting that equal to 0 and solving. What we solve for is the MLE. So by construction, this is true. So that means that the derivative of the log likelihood function, where we plug in the MLE, this is equal to 0, and that should be equal to, so now we've plugged in the MLE to the left-hand side. So anywhere there's a theta, not a theta star, but a theta, just here, we'll plug in the MLE. So we'll have the derivative of the log likelihood evaluated at the true value plus the MLE minus the true value times the second derivative of the log likelihood evaluated at the true value. All right, and now we can kind of see how we'll get part of this right-hand side. Right, we have the individual terms here, and it's just a matter of rearranging this equation. So this should imply that the negation of the log likelihood the derivative of the log likelihood evaluated at the true value, divided by the second derivative of the log likelihood evaluated at the true value, is equal to the MLE minus the true value. And then, so I kind of blocks out the negative sign here, so let me emphasize that. This should be negative. And then, so really what we're missing is the square root of n here and these terms here. So if we multiply on both sides by the square root of n, the one thing to note is that this, so 1 over the square root of n divided by 1 over n, is equal to multiplying these two by the square root of n. So if I were to multiply just this whole term by the square root of n, I can break that up into this numerator, 1 over the square root of n and 1 over n. So that should prove the result. We started out with this equation. We plugged in the MLE, and we were able to prove this equation. All right, and as I said, we'll now think about where the numerator and the denominator converge to in distribution and in probability, and then we'll use Slutsky's theorem to tie these together. All right, so let's work on that numerator. So this was the numerator from the previous slide. The goal here is to show a few things, actually. One is to show that we can write this term under our assumptions and regularity conditions as the square root of n times something that looks like a sample average. And we might actually just call this whole term, its square brackets, W bar, because it's the average of these W's, where the W, each W, is the first derivative with respect to theta of the log of the marginal PMF or PDF of your data. All right, and so what we want to do is show that the numerator from that equation on the previous slide can be written like this, and then we also want to show that it has mean 0 and variance Fisher information. And I think it's worth being a little bit more explicit here about which Fisher information. So the Fisher information for a single data point. So here I'm using I1 to denote the Fisher information for a single data point, the one associated with the marginal PDF, rather than what we could call IN, which is the Fisher information for the entire sample. All right, well, let's see how to do this. So first, 1 over the square root of n times the derivative of the log likelihood function evaluated at the true value. So 1 over the square root of n, I think it'll be helpful to write this derivative. I write them as partial derivatives because theta could technically be a vector rather than just a single value. But so partial derivative with respect to theta of the log of the joint PDF or joint likelihood. So that's just using this alternative notation. And we are operating under the assumption that our data are IID. So in particular, they're independent observations. So that means that this joint PDF was constructed by multiplying the marginals together. So we're going to use that fact here. So 1 over the square root of n times the derivative with respect to theta of the log of the product, so capital Pi for product from I equals 1 to n, of the marginal distribution. All right, and then the next step is to just use properties of logs. So this is the natural log of a product, and that's equivalent to the sum of the log of each of the factors. So we still have this 1 over square root of n hanging out front. Then we have the derivative with respect to theta, and now we'll have a sum of the log of the marginal. All right, and then the last step, so of course this is a sum from I equals 1 to n, so this is looking a good bit like this here. If this is a w, except we're missing the derivative, but the derivative is outside of that sum. That's easy to take care of. The derivative of a sum is the same thing as the sum of the derivatives of each term, so we can move that derivative inside. So I'll leave out the 1 over square root of n because we're going to deal with that in just a minute, so I'll leave some space for that. This should be the sum of the derivative with respect to theta of the log of the marginal distribution function. All right, and then the last thing to do is just notice that 1 over the square root of n is equivalent to the square root of n over n. So just using, properties of exponents. So this should be, maybe I'll move this over just a little bit. Square root of n times 1 over n. And so this whole term here is what I called w bar above. All right, so we've proved the first part. We've proved this equality. The next thing we want to do is just show that this quantity has mean zero and variance Fisher information. Well, the expected value of 1 over the square root of n times the log likelihood evaluated at the true value. And actually, I should make a note that in each of these here, each of these equations, I should be plugging in theta star, the true value, because that's what we plug in on the left side. So all of these thetas should be a theta star. And note that we're taking the derivative with respect to theta, and then we're plugging in theta star. So otherwise, it would be 0. All right, so what is the expected value here? Well, we know we can take constants outside of the expected value. And then this script L prime is the derivative with respect to theta of the log of the joint PDF, where we plug in theta after we take that derivative. Well, that should look familiar. This is something that we defined as the score, derivative of the log likelihood function. And this says take the expectation of the score. Well, we show that that's equal to 0. So this has mean 0. Now what about the variance? So the variance of 1 over the square root of n times the derivative of the log likelihood evaluated at the true value. Well, this should be, so looking at the derivative of this side, that should be the same as the, looking at the variance of this side, should be the same as the variance of this side. So we could write this as the variance of the square root of n times w bar. Well, we know constants come outside of the variance squared, so that square root of n will come outside of the variance as n, and this is the variance of w bar. So n times the variance of now 1 over n times the sum of the derivative with respect to theta of the log of the marginal distribution function. All right, well, we can still work with some of these, some things going on here. So this 1 over n will come out as a 1 over n squared, and so we'll get a cancellation here. And then again, because we have independent data, the variance of the sum will be equivalent to the sum of the variances. All So under independence, so if we have n over n squared, we'll be left with 1 over n times the sum of the variance of the derivative with respect to theta of the log of the marginal. Okay, so let's take a look at this. Well, this variance here is just the definition of the Fisher information, right? The Fisher information is the variance of the score. Now there's a subtlety here that this is the marginal, and that means that if we take the derivative, the log of the marginal, we don't get IN, we get I1, right? This is just the Fisher information for a sample of size 1. And we're summing these up, they're the same for each. So when we sum over them, we get n of them, so we get n times I1 of theta, but then the n cancels down here. So this term, this variance, is I1 of theta, and that means this whole thing is just I1 of theta because of the cancellation of the n's. Again, I should put my stars here. Yeah. All right, so I think we've proved all 3 points. The first one was this equality. The second one was that this quantity has mean 0 and has variance of Fisher information for a single data point. And the reason why we did this is because now we want to show something about where this converges to in distribution. So that'll be the next part of this proof. Well, here it is. So let's show now that, and I think we'll do it with this version, let's show that this converges in distribution to a normal centered at 0 with variance Fisher information for a sample of size 1. So I think we'll want to use the fact that we'll basically want to use the central limit theorem. So we know that the central limit theorem tells us that if we have a sample mean and we subtract off the expected value of that sample mean and we divide by the standard deviation of the sample mean, so I'll just write it as standard deviation W bar, this quantity under certain conditions by the central limit theorem will converge in distribution to a standard normal, a normal 0, 1. All right, so let's actually plug these values in. So first, the expected value of W bar is 0, and that comes directly from a calculation on the previous slide. So the numerator will just be W bar. Now the standard deviation of W bar will be the square root of the variance. And what's the variance of W bar? Let's see. So we sort of did it on the last slide, but there's just a constant difference there. So variance of W bar will be the variance of 1 over n times the sum of each of the Wi's. So we'll have 1 over n times, let's do 2 steps at once, so 1 over n squared times the sum of the variance of each Wi, and this is because of the independence condition that we can sum over the variances. And this we should have n times I1 of theta star over n squared, which is equal to I1 of theta star over n. So down below, we should be dividing by I1 of theta star over n. All right, so again, we know by the central limit theorem that this converges in distribution to a normal 0, 1. This is just plugging in the right values. And now the next step will be to multiply by the square root of n in the numerator and in the denominator. That won't change anything, obviously. It's multiplying by 1. But it will allow us to see the convergence and distribution of this quantity up here. All right, so the numerator is square root of n times w bar. The denominator will just simplify to the square root of the Fisher information for a single data point, because those n's cancel. All right, and we know, because all of these are equalities, and that this first part converges in distribution to a normal 0, 1. So we have convergence to a normal 0, 1. And that means that if we were to multiply basically on both sides here by this term that does not depend on n, then we would just end up with a different variance over here. So if we multiplied by the square root of the Fisher information on both sides, the left side would be the square root of n times w bar. We'd still have convergence and distribution. So it would be, think about this as some z, which is normal 0, 1. If you multiplied that z by the square root of the Fisher information, you'd end up with a distribution that's normal 0, but variance as that Fisher information. And that should prove the result, right? This shows that our quantity, square root of n times what we called w bar, converges in distribution to a normal 0 Fisher information. All right, so just to kind of recap what's going on here, we proved that this quantity that will get us the asymptotic distribution of the MLE can be written as this crazy looking fraction, and we just showed that the numerator converges in converges in distribution to a normal 0 Fisher information. So it's a Fisher information for a sample of size 1 and evaluated at the true value. All right, so now I think we're going to deal with the denominator. We want to show that the denominator converges in probability somewhere, and that will allow us to use Slutsky's theorem. All right, so let's prove this claim, this convergence in probability claim. So we'll start with the left-hand side, and we'll write it out in terms of the log of the distribution function. So this will be negative 1 over n times the second derivative with respect to theta of the log of the joint distribution function. And we're going to use the same trick that we used just a few moments ago, where if we have independent and identically distributed data, then this is constructed from the product of the marginal distributions. And if you have the log of a product, that's the same thing as the sum of the logs. And then, of course, you can take the derivative inside of that sum. So there's kind of a few steps that we're doing together here, but I think you should be able to follow them based on the previous slide. This should be negative 1 over n times the sum of the second derivative with respect to theta of the log of the marginal distribution. We've got to keep our stars here. All right. Well, this looks, without the negative sign, it looks like a sample mean. All right, you're summing up some terms and you're dividing by the number of terms. So, if we called this, each one of these terms, like a VI, then what we have here is negative 1 over n times the sum of these VIs. So you could call that a V bar. Well, we know that under the conditions that we're operating under, basically an IID sample, that this should converge in probability to the negation of the expected value of VI, and that's true by the weak law of large numbers. Well, what is the expected value of VI? So let's plug that in. Well, each VI was the second derivative of the log of the marginal distribution. And this is basically the definition of the Fisher information. So it is the Fisher information. The definition was the variance of the score, but we had some simplification rules that said we can write that as the negation of the expected value of the second derivative of the log likelihood. And here this is the likelihood for one data point. So this term here is just the Fisher information for a single point, a single data point. So if we put this together, it reads that this term, right, that we wrote out in a slightly different manner, we use some properties, like we had IID data, and we get to the point that we have this quantity converging in probability to the negation of the expected value, and that negation of the expected value just is the Fisher information. So we've proven this result. Okay, so let's put all this together. So ultimately we want to show that this left-hand side converges in distribution to a normal zero Fisher information, and then we can extract from this quantity the distribution of the MLE. Well, we showed that the top converges to a normal Fisher information, sample size 1, and that the bottom converges in probability to a Fisher information, sample size 1. So putting this together, I think it's easily seen that all of this will converge in distribution to a normal 0, 1 over the Fisher information of sample size 1. And the way that you get that is think about a random variable with this distribution, maybe call it y, and then think about the distribution of y over a constant, the Fisher information. The distribution of that quantity will still be normal. So you're just taking something normal and you're dividing it by a constant, still normal. The mean of that distribution y over the Fisher information will still be 0 because the mean of the original y is still 0. And then just compute the variance of y over the Fisher information and you'll get 1 over the Fisher information for that variance. All right, so I'll leave you to do that little bit of work on your own. So now we have, putting this together, we have the square root of n times the MLE minus the true value converges in distribution to a normal 0, 1 over the Fisher information. And we just have to deal with this quantity here. Right? This is part of the standard error of the MLE. The other part of it is down here. So just unpacking this, right, we can extract an asymptotic distribution from this convergence and distribution statement. So this should imply that the asymptotic distribution of the MLE is normal, and the mean you can read off here as theta star, so this is just definition of asymptotic normal. The variance is read off from this quantity also. Usually we see it as not multiplied by the square root of n, but divided by 1 over the square root of n. And so this n would get multiplied by this denominator. All right, because this whole thing is part of the standard error. The constant is part of the standard error of the MLE. So we should multiply by this constant to get the variance of the asymptotic distribution. So this will be 1 over n times the Fisher information for a single data point, but this is equivalent to a normal distribution centered at the true value and variance of Fisher information for the whole sample. And that's because n times the Fisher information for a single point is exactly the same as the Fisher information for the full sample. And then we just note that the Cramer-Rao lower bound in this context is just 1 over the Fisher information. That's something we proved in class a while back. All right, well, that was a long proof over multiple slides, but what we were able to do is do a bunch of algebra and then prove some different convergence results, and then finally show that from those convergence results we have a certain asymptotic distribution.